we're going to go over right now is kind of similar to some stuff that we covered in the. We sort of touched on some of these ideas in the first chapter, the very first lesson that we had. But we can have conditional statements. That have a hypothesis, which is our if statement, and a conclusion, which we call our then statement. All right. So this is kind of construction of a conditional statement. It'll be if this is true, then this must be true, right? And we call the if part our hypothesis, and we call the then part our conclusion. All right. To make another term that we need to know as far as conditional statements go is we need to know the term converse. So when you talk about a converse, you just switch, let's see, to make the converse, switch the hypothesis and conclusion. All right. So, for example, if Evan is yawning in class, then Evan didn't get enough sleep last night, right? That's always a possibility, all right? And so let's write, how would I say the converse of that? If all I'm doing is switching the hypothesis and the conclusion.
Evan did not get us enough sleep last night. Then, wait, sorry.
You're right, that's the...
Evan did not get enough sleep last night, therefore he is yawning.
Yeah, then he's yawning in class, right? So yeah, we just switch those around. Using the same if then, we do hypothesis and conclusion. I mean, hypothesis, not hypothesis. Hypothesis and conclusion. So does that make sense to you?
Yes.
All right. So that's the construction of a conditional statement. We need to know how to do the converse. And then we use negation. So that's another term we need to understand. Use negation to write the negative of a statement. So we're just putting a bunch of definitions up here first to make sure that you understand. So if we say, for example, the measure of angle A, draw my little angle symbol, that was terrible. Redo that. So the measure of angle A is equal to 30 degrees. If we wrote the negation of that statement, we would just say the measure of angle A is not equal to 30 degrees, all right? Do you know how we would do not equals in math?
Is it like an equal sign with a line through it?
Yeah, exactly. So it's not equal to 30 degrees. So that would be the negation. This is the negation of the first statement, okay? So we're gonna do some examples in just a second. I'm just gonna throw a bunch of definitions on the board and then we'll walk through some examples here. Why did I talk about negation? Because you can do this thing where you negate a hypothesis and a conclusion. So if negate hypothesis and conclusion, you get what we call the inverse. Okay? And if you negate I'm gonna do my little, have I done this with you guys yet? A little.
Yes.
Okay, so if we negate the hypothesis and conclusion of the converse, get what we call the contrapositive. Okay, so I think that's basically all the definitions I want to get through in this chapter. So, for example, to use our totally bogus example of if Evan is yawning in class, then he did not get enough sleep last night. Is that how I said it, or was it the other way?
If Evan was yawning, yeah, that's right.
Is that okay? So if we do the inverse of that, we would say that Evan was not yawning in class, so he got enough sleep last night. Right? That would be, we do the opposite of both of those statements. And then if we switch it around and we say Evan got enough sleep last night and so was not yawning in class, so that would be the contrapositive. Right?
Okay.
Is that we flip it around? All right, we're going to do this in a much more mathematical way. I thought I would make up this random one that didn't make any sense, you know.
Sure.
I actually haven't seen you yawn, so you're actually good. You may be yawning on the inside, or you're doing it when I turn around. All right, so let's look at chapter 2.1 and just do some examples here to make sure that we can do problems where they're asking us to construct these. And we've actually got a whole bunch of postulates we haven't even touched yet. So yeah, we're gonna have to do a bunch of those. But let's just try rewriting some of these statements in here and doing an if-then, a conditional statement, and then doing the converse, all that good stuff. So let's just go directly to, let's do example 3. That's kind of a good one, I think. So if two segments are congruent, they just ask us to write the converse of this. So if two segments are congruent, then they have the same length. So what we know about the definition of a converse, how would you reword that to be the converse?
If two segments have the same length, then they are congruent.
That's right. So we just flip them around, right? Now, how would I, if I want to do the inverse of our conditional statement, what would that be?
If two segments are not, yeah, if they're not.
We negate both the hypothesis and the conclusion when we do the inverse. So you're right.
If two segments are not congruent, then they do not have the same length.
Right, exactly. And then if I want to do what we call the contrapositive, or wait a minute, I'm sorry. Is that right? Yeah, the contrapositive. I'm going to not the whole thing, but flip it around, right? So tell me what contrapositive would be of that.
If they do not have the same length, then they are not congruent.
Exactly. That's exactly right.
Two segments.
Okay. So let's do it kind of mathematically. Let's just write this down to make sure that you can see this. So here's our original. All right. We'll kind of put lines here for each of these. We've got our original, and we've got our inverse, and we've got our converse, and our contrapositive. All right, and they say the original is if the measure of angle A equals 30 degrees, then angle A is acute. All right? So the inverse of this, that's your column up there. I'll take a bite of my egg. My wife so lovingly made for me this morning.
Converse would be if angle A is acute, then angle A is equal to 30.
Yes. So if angle A, that's okay. This is good. This is kind of how we learned it. So if angle A is acute, then the measure of angle A equals 30. Right. So now let's do the inverse and the contrapositive of each of these.
Okay. The inverse would be if angle A does not equal.
So the measure is still the measure. So
measure
of angle A,
measure
right, does not equal. We would use this symbol here. 30 degrees. Good.
then angle A is not acute.
then angle A, right. Okay, and then of course this one, same thing, but just in the reverse order, right? So angle A is not acute. And measure of angle A does not equal 30. All right? All right, so just kind of note here, if we think about this, if the measure of angle A is 30 degrees, then angle A is acute. Is that a true statement?
Yes.
That is true, right? So this is true. What about this one here? If angle A is not acute, then the measure of angle A does not equal 30 degrees.
Yes. Also true?
If it's not an acute angle, then clearly it can't equal 30 degrees, right?
Mm-hmm.
Because it's got to equal either 0 or somewhere between 90 and something greater than 90, right? So the point to that is that if this statement here is true, then the contrapositive will also always be true.
Okay.
Okay?
Right. If you did the contrapositive.
That's right, if we did the contrapositive to an original statement that's true. But now let's look at the inverse and the converse. If the measure of angle A does not equal 30 degrees, then angle A is not acute. Is that necessarily a true statement?
If yes. Wait, you said the converse or the
This one here, the
yeah,
inverse.
no, I think that is true.
If the measure of angle A does not equal 30 degrees, then we can say without a shadow of a doubt that angle A is not acute. So what if angle A equals 31 degrees or 20 degrees?
Sure.
Right? It's not 30, but is it acute?
Yeah.
It is, right? So this is actually false,
Okay.
right?
Okay.
And what about this one? If angle A is acute, then it must equal 30 degrees.
So that's also okay.
I mean, that's one case, but again, if it was 31 degrees, it would still be acute, but it wouldn't equal 30, right?
Right.
So these here, whatever these are, the other will also be as well. So if these are both, if this first one's true, then this one will be true, but if this one's false, this one will also be false.
Okay.
So that's just kind of something that you can remember with the way these are laid out. And also, in order to disprove any of these, all you have to do is give me one example. Right? We talked about that, and that's where we kind of go back to what we learned in section 1.1. If you can give me one example that makes it not true, then the whole statement is considered to be not true. Okay?
Right. Okay.
And they just make a note in the book that these are what we call equivalent statements, because they're another way of saying we're just rearranging the way that we say this, but both of them are true. Or in this case here, we're rearranging the way we say this, but both statements are false. So we refer to these as equivalent statements. All right?
It's kind of an if-then statement too. Is if original is true, then contrapositive is true.
Exactly. That's good. That's good. You're using the language that we learned, right? All right. So let's write down. We got a bunch of postulates that we just have to know. Let's see if I want to write all these down. Just for time's sake, I don't think I'm going to write these down. How are we doing on time? Oh yeah, we've already got like 30 minutes. We spent a lot of time reviewing the quiz.
Oh wow. We only have 30 minutes?
Yeah, it's like 9:58 already.
Wow.
So I'm not gonna write this down, but make sure no. If only I could write. Make sure, that's what happens when I get in a hurry. Make sure no postulates on page. So we'll just talk through these real quick, but I'm not going to write them down, okay? These may be things that you want to write on your note card for the test, right?
Okay.
I told you guys these boxes here, and anything that's bolded in the chapter, that's good stuff to write down. A lot of times, make sure you understand that information.
Okay.
In fact, that would be a great way when you're doing your homework. Like go ahead and start on your note card, right?
That's a great idea.
Do your homework, and if it's like I need to look this up, let's write it down on the note card, and then you can use your note card as reference for another problem or something, right?
Sounds good.
So postulate 5 says through any 2 points there is exactly one line. So just make sure that you recognize that. If you've got 2 points, there will definitely be one line that goes through those 2 points. A line contains at least 2 points, so we can't even sort of identify a line unless we have a couple of points, right? I have no way, if I say here's a point, draw the line that goes through that point, well, you're like, I could draw all sorts of lines that go through that point. If you're asking me for a specific line, I've got to have another point to know where that line is, right?
Right.
If two lines intersect, then their intersection is exactly 1 point. Through any 3 non-collinear points, there exists exactly one plane. So if we've got points like this, there is one plane that you basically need 3 points to identify where that plane is. So if you think about it, if I did a point here, here, and here, then the plane goes this way, right?
Right.
If I label 3 points, it'll be clear to you that that's where the plane is. That should be enough to identify that plane. A plane contains at least 3 non-collinear points. If 2 points lie in a plane, then the line containing them also lies in a plane. So that's sort of an important point. If we've got this line here that didn't go through my points at all, see the math trick for this is you just erase your points and move on to the line.
Genius.
So if these 2 points are on the plane, in this case here the plane is our board, right? Then the line that those points are contained in also has to be on the plane. So again, that's some of this stuff is just sort of obvious, but they're making postulates out of it. And part of the reason we're making postulates out of it is so when we do proofs, like I was talking about, we can go back and say, according to postulate number 10, this is true, right?
Which is why it's helpful to have a note card telling you.
Yeah, exactly. Are you going to remember postulate number 10? I'm not going to remember that. And if 2 planes intersect, then their intersection is a line. So there's a diagram there on at the bottom of page 73. And that kind of shows you what that looks like. And do you see how those 2 planes intersecting, there's going to be a line that goes through that intersection?
Yes.
Right? So yeah, they're just, that section down below there is just identifying regions in that drawing that uses those postulates, so to make sure that you understand what those postulates mean. So I'm going to give you some homework to practice that, but are there any of those postulates as we read through them that you're like, I don't really understand what that's talking about?
No, they are pretty
Yeah, they're simple ones, but just the language may be confusing. So
right.
We can talk through that if it's confusing.
Thank you.
But you think it's good?
I think it's good.
Okay. All right. Well, let's move on to section 2.2 then.
I'm waking up a bit more. So.
Okay, good. 2.2. So let's see. This is actually kind of a quick section. So that's good for us. We've got a couple lines like this. And they intersect. What does it mean whenever I put that symbol there?
It's a right angle?
It's a right angle, which means it's how many degrees?
90.
90 degrees, right? So do you know then what kind of lines these are?
Are they rays?
Well, these would be rays only if we kind of consider the point from the middle out,
okay.
Right? But these 2 lines, like if I label this P and Q, there's a certain thing that we call line P as it relates to line Q. Do you know? You may not have seen it before. I can't remember where you've learned this.
Yeah, I don't
All
know.
right. So these are called perpendicular lines.
Oh.
Do you know that term?
Yes. Okay.
Okay. I thought maybe you had gone over that, at least in algebra, but I wasn't sure. So perpendicular lines, by definition, they intersect to form a 90-degree angle. Okay?
Okay.
So that's our definition of a perpendicular line. And we can write that as, we could say line P is perpendicular to line Q. So that's the symbol that we use for it. It's like an upside down T.
Okay.
If a line happens to be perpendicular to a plane, and do I even want to attempt to draw this? Let's see. So here's my plane. And we've got a line that maybe goes through here and then comes out this side. All right. So if that line, and well, we gotta imagine that it's perpendicular. I still don't know if I've done that well, but I don't even know how to really draw that.
Yeah, that's right. It's hard to do.
Okay. So if we know that that line is perpendicular to the plane, then we know that any line that's in this plane, right, then this line is also perpendicular to it. And so that's all that statement's saying. So I don't know where we might need that, but that should kind of be obvious to us, right? If I had a, like if this is your plane, right, and we consider this pin to be our line that goes through it. And so if it goes through it like that, it's clearly perpendicular to the plane, right? It forms a 90-degree angle. So do you see if I drew any line on that piece of paper, this line would also have to be perpendicular to every line that was on that piece of paper?
Yes, because it would always, okay.
All right, does that make sense to you? There would always be a 90-degree angle. You know, even if I did, like if this was my line, it was coming in like that, still, this measure from here to this line here is still going to be a 90-degree angle, right? So if it's perpendicular to the plane, it'll be perpendicular to every line in that plane, okay?
Okay.
And then, now we talk about biconditional statements. I didn't realize that was in this section. Okay, so let's do a couple of examples about perpendicular lines first. Look at example 1, which is on page 79.
Yes.
And they just want us, don't look at the solutions down there, but let's just look at the top part. All right, and tell me if these are true or false. Points D, X, and B are collinear.
True.
That's true, right? They all lie on that line that we could say was line DB, right? AC is perpendicular to DB. I'm sorry, line AC is perpendicular to line DB.
No, I think so.
We don't have to think. We can know with certainty because they tell us what the angle is between those two lines. What do they tell us is the angle?
Wait, they do? Where?
Because they put that little box there.
So yeah.
If that box is there, remember, if you see that, that means without a doubt that that's a 90-degree angle, right?
Okay.
And if we see two lines and we know the angle between those two lines is 90 degrees, we know for sure that they're perpendicular. Okay, by this definition here. Does that make sense?
Okay. Yes.
Okay, so do you see why there's, so line AC, which is that line, has to be perpendicular to BD or DB, however they do it, because they tell us that the angle between the two is 90 degrees. Okay?
I mean, they're not parallel, so.
That's right, they're not parallel. If they were parallel, there would be nowhere that they intersect. Right?
Which I've always just thought of perpendicular as the opposite of parallel.
That's right. Yep, that's a great way to think about it. In fact, when we learn about slope, and you may have already learned about that, but it's you kind of see in one sense how the slopes are opposite one another. But anyway, that's a different day. And then the angle AXB, all right, the angle, let me just write that on here so we can see that. All right, well, actually, I can just use our existing drawing. D, this is D. That's what I should have done. Just used my, trying to save time, and it was already here. All right, so here's our point. So they tell us that angle AXB, this is X. So angle AXB is this angle that's formed here, right? And they say that that angle is adjacent to CXD, which is the line, which is this angle here. Are those adjacent to one another? What was our definition of adjacent?
What was our definition of adjacent? It was lines that. Well, I can listen. No.
They are not, because adjacent lines share a common side. All right. So like we basically got an angle that looks like this, and we've got another angle that looks like this. They share a vertex, right? They both meet here in the same point,
right?
But they don't share a common side. These sides here are totally distinct from these sides here. Right? The side, right? Does that make sense? So if they had been like this, like if it had been these two angles, angles 1 and angle 2, we would say those were adjacent because one of their sides are the same.
Right.
Make sense?
Right.
Okay. Cool. So I don't know if you want to write something down about that. You did,
yeah.
Just to make sure that you don't lose that, because that's definitely a concept that's going to be on the test you're taking home. All right.
Right.
I want to make sure you understand that. All right, let's talk about biconditional statements. So, a biconditional statement contains the term if and only if. All right, and so let me just go ahead and label for you that this is the shorthand way that I'm going to write if and only if. So that IFF equals if and only if. Right? So that's kind of our way of saying if this and only this is true, right? There's not any other option. If you say, if I write IFF, it means that's the only case. So a biconditional statement is one where we can say if and only if. So it contains IFF. It is equivalent to writing a conditional statement and its converse. So we put those together. That's how we will construct our biconditional statements. So we write a conditional statement and we put it with its converse. Okay?
Okay.
So if I ask you to write a biconditional statement, that's what I'm asking you to do. Put those two together and use the phrase if and only if. Alright, so I'm just kind of thinking back on what we did the last chapter. So we put the conditional and its converse together. And so yeah, we wouldn't put those together because those were one set was false and this one was true. So let's try another example. So they note that you don't have to use if and then always for conditional statements. They don't always use that form. You may sometimes see the only if form. So if, not if, I'm sorry, I did it wrong. I just said we weren't using if then. It is Saturday. Only if I am working at the restaurant. Do you have a job?
No.
Okay, I wasn't sure.
Unemployed for 16 years.
Alright. So you could rewrite this in if-then form by saying, if it is Saturday, then I'm working at the restaurant. Okay?
Right.
But this would also be a conditional statement here, so you may see it sometimes in that format. All right. So if I were to say, were to write this as a biconditional statement, what's missing?
The if
and only if, right? So it is Saturday if and only if I am working at the restaurant. So if I wrote it like that, it is Saturday if and only if I am working at the restaurant. Then by writing it as a biconditional statement, what I'm saying is that I only work on Saturday. Right? Does that make sense?
Yes.
So if I'm working at the restaurant, you know today is Saturday because that's the only day I work. So that's how definite if and only if statements are, right?
Okay.
So so let's example 2. We're just gonna kind of read this rather than write it all down. And let's see if you can do that. Don't look at the conditional and the converse. Remember, what did we say? Biconditional statements put the conditional and the converse statements together, right? So let's see if we can just do that from the biconditional statement that they give us, right? So they say 3 lines are coplanar if and only if they lie in the same plane. So let's do the conditional statement first. And remember, the conditional statement is it's on page 80.
Sorry.
All right. See example 2 there?
Yes.
Okay. So just look at the 3 lines are coplanar if and only if they lie in the same plane. All right. So the conditional statement for that, we're going to just make an if-then conditional statement from that. So how would you make that to be an if-then?
If 3 lines are coplanar, then they lie in the same plane.
That's right. So we just put the if and the then, remove the if and only if, right? Now remember, the converse
is if they lie in the same plane, then if 3 lines lie in the same plane, then they are coplanar.
Okay. All right. Good. So yeah, we just flip it around, right? We put the same plane part first and the coplanar part last, right? So do you see how if you take those 2 and merge them together, that's where we get the if and only if statement. Make sense?
Yes.
All right. So when we look at example 3, let's see if this is, consider x equals 3 if and only if x squared equals 9. All right, so we've got that biconditional statement there. We know it's biconditional because it's got an if and only if statement in it. Mm-hmm. The first question they ask us is this a biconditional statement? Yes, it is, because it's got if and only if, right?
Right.
So the second one is it true? And how do we determine if it's true or not? Well, we just have to see, can we come up with one example where that wouldn't be so, right? So x equals 3 if and only if x squared equals 9.
I can't think of another scenario.
So can we bust it, the way that you would check it would be to bust it up into a conditional and a converse statement and see if both of those are true. Okay. So if both of those are true, then this would be a true statement, all right? So let's think about it like that. If x equals 3, then x squared equals 9. Is that a true statement?
Yes.
That's true. Let's flip it around. If x squared equals 9, then x equals 3. Is that a true statement?
X squared equals 9. And x equals 3.
So if x squared equals 9, x equals 3. That's the converse. That has to be true for this thing here also to be true.
Right.
And so if we say x squared equals 9, and we solve for that, we have to take the square root of both sides. And so that gives us, but when we take the square root here, we have to say plus or minus. So x equals plus or minus 3. Right? Isn't it true that if x was negative 3, it would also equal, x squared would also equal 9?
Yes.
Right?
Yeah.
So this one here is not always true. Right? If x squared equals 9, x could equal negative 3 instead of positive 3. So this statement then is also not true. Does that make sense to you?
Mm-hmm.
Yep. All right. So those would have to both be true in order for us to prove that that thing was true as well. Does that make sense to you?
Mm-hmm.
How we can test that? So if they ask you if a biconditional statement is true, bust it up into its converse, and bust it up into the conditional statement and its converse, and then test to see if both of those are true. All right. That's our rule. Let me just write that down to make sure. It's definitely a note that you need. You know, I would put that on your little note card. To test if by conditional statement is true, verify conditional statement and converse are true. So that's how we would do that. Okay? last thing is it's kind of a similar idea, but we're going to use variables now to represent our if and then statements. So it makes it a little simpler, and we can use, it allows us also to kind of use some symbols to do some shorthand for the way that we're representing the original, the inverse, the converse, and the contrapositive. So let's see, in symbol notation, use P to represent your hypothesis, and Q to represent your conclusion. The symbol means implies. So I'll put the symbol in quotes too. So if you see that arrow, that just, you can read that as implies if you were reading a statement like that.
Okay. Use
this symbol for negation. So that's a tilde. It's usually like on the top left of on your keyboard on your computer.
Yeah.
We've seen the tilde symbol used one other place. Where is that?
Oh, I don't remember. But I do remember.
We've seen it used for this. What does that represent?
Congruency.
Congruency. So that means two things are congruent to one another. If you see a tilde all by itself, the way that we use that in this class is to mean not. Okay, we use it for negation. So given these symbols, we can now kind of write something what we did before, where we have our original, our inverse, our converse, and our contrapositive. All right. And we can say for our original, if we're using P and Q to represent our hypothesis and our conclusion, then if P, then Q. That's how we would write that.
Right.
Okay? Now, do you remember how we found the inverse from the original?
We did the opposite.
So we negated both of them, right?
Negate. Okay.
So then we would put a tilde in front of each of those. And that's how in symbol form we would write the inverse.
Okay.
Make sense?
Yes.
Okay. Now when we found the converse, we based that off of the original, and what did we do?
Flip it.
We flipped them, right? So how would I write the converse then using symbols?
So Q, then P.
That's right. Q, and I guess we would say implies. Q implies P, since we said that's how we read that arrow. So Q implies P.
Okay.
And then for the contrapositive, we took the inverse of the converse. So we just put the negation symbol in front of each of those.
Right.
Does that make sense? Just a shorthand way to represent the same thing, right?
Right.
So this to me is really helpful, especially on a note card when you have limited space,
Yes.
right? Rather than writing out the whole thing that you had before, just kind of, this is a shorthand way to do that. And they give us some, so they give us an example here. How we do on time? We're running short. Let me see. I need to introduce two laws to you, but let's just practice real quick with example 2. And they tell us in example 2, I'll leave the little chart up on the board, but they say P, let P B, it is raining. And Q, the soccer game. Do you play soccer?
I used to.
Okay.
I might later. I don't know.
I gotcha. That's one of those. We didn't have those back growing up in South Georgia. Like, we played at PE, but it just wasn't a thing. And
Right.
so when we moved up here, I was like, wow, there's soccer everywhere. We didn't have any soccer teams. I think they play it down there now, but it just wasn't popular when I was growing up.
Yeah.
So here's what P and Q are. So let's write statements. Write each of these statements based on these. So let's see if we can do that. So what would the original be?
It is raining. If it is raining,
Mm-hmm.
then the soccer game is canceled.
That's right. If it is raining, then the soccer game is canceled. All right. And so for time's sake, I'm not going to write the rest down, but let's just talk through those real quick. So the inverse, we negate the P and we negate the Q. So we would say,
if it is not raining, then the soccer game will not be canceled.
exactly, yep. And then the converse,
The soccer game is canceled. If the soccer game is canceled, then it is raining.
that's right. And then finally the contrapositive,
If the soccer game is not canceled, then it is not raining.
all right, cool. So this is, you see how the shorthand will help you? How this would be
Yes.
easy to write down on the card, and then as long as you understand what P and Q represent, it's really easy to build those. We need to cover two final laws, the law of detachment and the law of syllogism. So we'll start with the law of detachment. And law of detachment says if P implies Q is true and P is true, then we can assume Q is true. All right. So in other words, with P implying Q, the hypothesis implies the conclusion is true. If that's true and the hypothesis is true, then we can say that the conclusion is true. All right. So let's just do a quick example to make sure we understand that. And our example is taken from on page 89, example 2.3. And so the first one, this example 4, says Jamal knows that if he misses the practice the day before the game, then he will not be a starting player in the game. So the hypothesis is if he misses the practice the day before the game, right? And the conclusion is he won't be a starting player in the game. So he misses the practice on Tuesday, so he concludes that he will not be able to start in the game on Wednesday. Is that true? Well, what is P? P for this one is Jamal misses practice before game. Q is he will not start in the game the next day. And so what they tell us in this one is that, in fact, so this is the true statement overall. If he misses a practice before the game, he will not be able to start in the game the next day. And then they tell us that P is true because the next part says that Jamal missed the practice on Tuesday. So he concludes he won't be able to start the game on Wednesday. All right, so that's the law of detachment. The statement was true. The P and Q together were true. P was true. Jamal did indeed miss a practice before the game. So Q had to be true. He will not be able to start in the game. Now let's look at the next example. In the next one, it says if two angles form a linear pair, so in the next example, P equals two angles form a linear pair. If that's true, then we can say Q is also true, which says they are supplementary. All right. Now, they tell us next that angle A and angle B are supplementary. Angle A and angle B are supplementary. Is it true then that we could say angle A and angle B form a linear pair? Right? Is that a proper use of the law of detachment? And the answer in this case is no, right? Law of detachment applied just fine when we were looking at this one. It does not apply with this set of information here. Why? Well, P implies Q. That's true. That's our original statement. If two angles form a linear pair, then it's true that they are supplementary. All right. What does supplementary means? It means when you add them together, they equal 180 degrees. So that's true. But they didn't tell us right here that the hypothesis P was true. What did they tell us was true? They told us that Q was true, right? The conclusion part of our conditional statement was true. They are supplementary. This thing does not say if P implies Q is true, and if Q is true, then P is true. That's not how it reads. The hypothesis has to be true along with the conditional statement. Then we can say that the conclusion is true. All right, they gave us the reverse here. So we cannot say that this is true right here based on the law of detachment. And in fact, we can give you an example when that's not true, right? This statement would be true if we had something like this, where this was angle A and this was angle B. Sure, both of those angles are right here. They form a linear pair, and so therefore they are supplementary, right? Both of those angles are supplementary, and they do form a linear pair. But what if we drew angle A and angle B like this? Right, so this is A, and maybe we'll say this is, I don't know, this is 44 degrees, right? And then we'll draw angle B over here, and we'll say angle B is 46 degrees, okay? Now, those angles, when added together, they do indeed equal 90 degrees. So it is true that those angles are supplementary, just like it says right here, but it is not true that those angles form a linear pair. They're totally separate from one another. They don't share a common side and are formed by the intersection of a line or a line segment and a line, right? So this is not, we can't use the law of detachment to say this. We can use the law of detachment to say this stuff in the first part, okay? So let's move on to our final one. Law of syllogism. And that says if P implies Q, this one to me is easier to see, and Q implies R are true, then P implies R is true. All right, so they give this example here. If Mike visits Alabama, then he will go to Montgomery. All right, that's statement A. That's PQ. Right, this is PQ. Little thing there. All right. If Mike goes to Montgomery, then he will visit the Civil Rights Memorial. All right, so that's our example in the book there of what Q and R are. So this is Q and this is R. So do you see then if those two statements are true,
Yes.
then we could also see that P implies R.
Right.
Wouldn't it also be true then if Mike visits Alabama, then he will visit the Civil Rights Memorial?
Yes.
Do you see how that has to go together?
Mm-hmm.
So that would be our final P. So if I told you to use the law of syllogism to write the final statement here, you would say, if Mike visits AL, he will visit, and I'm just going to abbreviate that, CRM. There we go. Civil Rights Memorial. Okay?
Okay.
Clear?
Yeah.
Clear as mud?